So in this video, I'm just going to recap chemistry of haloalkanes. Got our different sections. I'm just going to go over label below. So haloalkanes are reasonably reactive, and they react with nucleophiles and nucleophilic substitution reactions. Just to recap nucleophiles, they are lone pair donators or donors. Examples that are involved in these types of reactions would be ammonia or amines, so lone pair on the nitrogen, hydroxide, which is the most common one, and we'll come to hydrolysis in a moment, but it's got to be aqueous hydroxide, or just water itself, which has got oxygen's got a couple lone pairs. We're only going to draw one on though. So we've got these lone pairs that can be donated to form a new bond. So that generally these place in hydrolysis, so that involves H2O or OH minus aqueous. So we've got that water in there, hence hydrolysis. And in our mechanism, depending on whether you have to do SM1 type mechanisms or not, I'm going to go through just the general basic one. If you do SM1, you go on doing it in the wrong order, but it doesn't matter at OCRA level. So carbon is delta positive, chlorine delta negative, because chlorine's more electron negative, so the electrons are pulled towards the chlorine in this bond. Then that creates a positive for this nucleophile to attack. So that's going to come in and attack that carbon. We draw a full arrow to represent the movement of a pair of electrons, and those electrons are the two on that lone pair on the hydroxide ion. Curly arrow from the lone pair, and then that also means we get a break in this bond, and the electrons from the bond, so the two electrons in this covalent bond, they both go to the chlorine. That creates our alcohol plus Cl minus, and this is nucleophilic because I'm using a nucleophile, substitution because I've substituted the OH for the Cl. Next up, bond strengths. So depending on the halogen that's attached, we get a different type of bond strength. So if we go with CF, these are the strongest, and as we go down, you get weaker and weaker. So the weakest is Ci that we're going to look at. So CF strongest, Ci weakest. So if we're going to do reactions with these, the weaker the bond, the faster they break, the quicker the reaction. So in reactions, this will have the fastest reaction because it's the weakest bond, and this will have the slowest. And we can measure that experimentally. We don't use CF in our experiments, so we can show it with C, Cl, Cbr, and Ci. And if we take each of these, and obviously going to be attached to a full compound, I'm just concentrating on this bond. In fact, I might just do them next to a methyl group. So X could be either chlorine, bromine, or iodine, but it's the same reaction goes on. If we do a hydrolysis, then what happens is we form our alcohol, our halogen breaks off and we get a halide, so a negative ion, and we also get H+. Now these are all aqueous or liquid, so difficult to actually see any reaction occur here. So what we can do is add to this original mixture silver ions. Now they're aqueous as well, can't see them, but as X minus, which was aqueous, gets formed from this reaction, it reacts with the silver and forms AgX, which is solid. So we'll see that appear as a precipitate. So we can measure how fast this reaction is by how fast silver halide gets produced. And not only can we identify how fast it's going, if we time how long it takes for the precipitate to appear, we can also use it to identify what our original X was, because chlorine will appear white and it'll appear slowly. Bromine will appear cream and it'll come a bit quicker than chlorine. And iodine will be yellow and it will come the fastest of the three. We can also measure the rate of whether it's first, primary, secondary or tertiary. So here we've got bromine attached to the same number of carbons, just isomers of a bromoalkane. So we've got primary, secondary and tertiary. In this one, this is the slowest, the primary, and the tertiary is the fastest. And it's to do with Markovnikov's rule that we saw with alkenes. How stable is the intermediate? And if this bromine breaks off, we get this intermediate. Compare that to this intermediate, and because this carbon's only bonded to one carbon, this is unstable compared to this intermediate, which is more stable. So this can deal without the bromine better than the primary. So the tertiary goes a bit quicker because it doesn't mind as much losing the bromine, whereas this one, because it hasn't got a stable intermediate, wants to hold on to that bromine a bit more. And that is a recap of haloalkanes.